Chair for which session?
Well, I mean, just in general.
It's Julia. Yeah. I just had to share the screen, it wasn't sharing. Yeah. Yes, yes, yes.
That should be better. Can people online hear? You can put it in the WebEx chat. Rachel? Okay. If somebody online can turn on their video and give us a thumbs up, okay, great. Should be better. Maybe the mic closer to me? All right. Okay, great. All right, so welcome to the Ulysses workshop. I'm going to have a few logistical announcements to do, but before, I would like to introduce our director, Jennifer Lotz, who is going to give us some welcome remarks before we get started at 9:15 with our first speaker. So, Jen, the floor is yours.
Good morning, everyone. Can folks online hear me? It's my great pleasure to welcome everyone today to this workshop to move forward with this director's discretionary policies. Space Telescope director's discretionary programs have a really great legacy, starting with the Hubble Deep Field in 5, South, which actually included a very deep spectrum with STIS. There we go, green light, thank you. The Hubble Deep Field South, which included a very deep spectrum of STIS. The Ultra Deep Field, the Frontier Fields, which I had the pleasure of being the local PI for. And now we have the Ultraviolet Legacy Library of Young Stars Essential Standards, which has been going since about 2020. These programs are really special in the sense that the director has the opportunity to try to do something different, to create and enable ambitious science by really trying to push Hubble's capabilities in a way that's done with the community for the community to create these legacy data sets. And I know Ulysses was inspired by the need to really push on our ultraviolet spectroscopic capabilities with the idea that Hubble has these really unique capabilities. So Ulysses leverages HST's unique spectroscopic capabilities to study massive stars and nearby low metallicity galaxies and young and accreting low mass stars. The science impact is broad, as shown by the really diverse set of talks that you'll hear this week. And it was designed by the community for the community in collaboration with folks here at the Space Telescope Science Institute. This is the largest director's discretionary program ever executed with Hubble, and in fact, the largest program, over 1,000 orbits. And the data releases are now complete as of December. So I want to say congratulations to Julia, her team, and everyone that's contributed. I know from experience that's a huge milestone. Analyzing and reducing and setting up 1,000 orbits of DD time is really a big deal. So the goal for this workshop is to bring this community together to move forward with this amazing data set and foster new ideas across a really broad range of science. I wanted to say a few words about how Hubble's doing. We're about to have the Cycle 32 call for proposals, as I'm sure many folks here are aware. It's really going as strong as ever. So in 2023, we had the highest number of publications ever, over 1,000 publications. Cycle 31 oversubscription was 6-to-1, and funding requests were much more than we could handle. If we look towards the future, Hubble's telescope, its gyros, its instruments really have a very high probability of continuing through 2030 and beyond if we're able to provide sufficient operation support. And Hubble is a really important bridge to the next generation, the Habitable Worlds Observatory, which we don't expect to come online until something like 2040, particularly for UV science, where Hubble remains, will continue to have this unique capability. So as many of you should know, one of the top recommendations out of Astro 2020 was to further the technology development that would be needed for Habitable Worlds Observatory. This has two main goals, which, when put together, result in a really incredible observatory. to find the signatures of life on exo-Earths, which would push the technology development to extreme, requiring 10 to the minus 10 contrast ratio for coronagraphy, as well as ultra-stable control of the telescope. But also looking, using that amazing capability and aperture for general astrophysics, which would include having a very large diameter mirror and UV capabilities, UV high-resolution spectroscopy, which would surpass Hubble, and UV and optical imaging, which would complement what James Webb is already doing. So for the young folks in the room, I really encourage you to stick around for the last day and to be engaged in some of the discussions about the next generation observatories and this hack session for the Precursor Science for Habitable Worlds Observatory. So with that, I just want to again say welcome. I think this is going to be a really exciting week, and I look forward to seeing what comes out from this meeting and what new science will be done with Ulysses and Hubble. Thanks very much, Julia.
Yep, I'll say a few more words. For those who haven't met me yet, I'm Julia Romandeval. I'm the Ulysses implementation team lead. And I wanted to give a few more specific details on the goals of this workshop. There are twofold. One is to provide a status update on ongoing work that is related to Ulysses, either using Ulysses data or ancillary data or theory, but also to provide a forum to you all to plan a roadmap for future analysis to make sure that we really exploit the Ulysses data to its fullest potential and really fulfill the promise of this very large investment of Hubble time. And so here we are. So thank you all for participating either here or online. It's been a long time coming for us, the implementation team at STSEI. This is really 4 years of hard work coming to an end. But for you, it's just the beginning. No pressure. And so welcome. I wanted to thank our scientific organizing committee, which is composed of Alex Fullerton, Will Fisher, Joe Taylor, Ravi Sankrit, Charles Prophet, Sarah Betty, Callum Hawcroft, Miriam Garcia, and Catherine Espayat and Greg Herksek, all of whom are either here or online. A huge thanks also to Sherry Tahana, Shemaya Smith, and Thomas Marufu, who's in the back there running the show in the AV. They have worked out all the logistical details of this workshop, and it's a lot of work. So I wanted to thank them. You'll see that the program, which is posted online, is organized by topic. And I think this is really an opportunity for the different communities that are gathered here today, Low MyStar, High MyStars, ISM, CGM, and whatnot, to really have an opportunity for cross-fertilization and get new ideas. And so I hope that even if a session is not exactly your field, you stick around, you hear what's being done in other fields with the Ulysses data. In terms of, I have a few logistical items to discuss. The contributed talks are 12 plus 3 minutes. The invited talks are 45 plus 5 minutes. And I encourage you to do your best to try to stick on schedule so we can all finish around 5:15. There are poster boards out in the cafe where poster presenters can display their posters for the whole duration of the workshop. We should be able to fit 3 posters on each side of each board. And we'll have poster pops at the end of each day to allow poster presenters to introduce themselves and their work. We'll display the electronic version of the poster, and they'll have roughly 1 minute to present it. I hope you all got an invitation for the Slack workspace. This will be a platform to ask questions, discuss, post the talks and posters. And also on Thursday, we have 2 formally planned hack sessions, one on Habbo's precursor science cases, as Jennifer said. Another possible one on more in-depth walk through Ulysses data, but also if you are willing to self-organize into collaboration meetings or different hack sessions or any topic you want, please let us know and we can make it happen. We can have a room and a chair and basically coordinate the logistics for this to happen. On Tuesday afternoon, there will be a data product session led by Joe Taylor, Rachel Plesha, and Ellen Fraser. I really encourage you to attend this. This is going to be a very hands-on walkthrough Ulysses products, and these products are very powerful, and hopefully this session can teach you how to make the best use of it, and should be actually very helpful for future analysis of Ulysses data. We'll have dinner at Gertrude's on Wednesday at 6 p.m. The talks will finish around 5, so there'll be an hour to, maybe hang out, walk there. I think we're going to have SDS also in the cafe. Rachel, can you confirm that? Yes? Okay. That's like a beer thing that people will hang out and it's fun. So if you want to spend a few minutes there and mingle with STSCS staff, that would be very welcome. And then finally, we want to ensure a very pleasant experience for everyone. So I encourage you to check out the ground rules for respectful discussions that Sharita posted on the general Slack channel. And of course, let's all be respectful, courteous, professional. Let's not talk over each other, etc. And finally, I really encourage young researchers, early career researchers to participate in the discussions and ask questions. There's no such thing as a bad question. If you are wondering about something, chances are a lot of people in the room are too. And so ask questions, speak up, and enjoy the workshop. For our first session, Ravi Sankrit will be chairing and Rachel Plesha will monitor the Slack and WebEx. And Noria is the first speaker. You want to get set up?
No, she has to introduce me. She has to call on me, right? Yes. I didn't know it was supposed to. Yeah, this is it. We already went through it. Yes, please. I can do that.
Okay, is this working? Yeah, so good morning. The first session will be overview of Ulysses in general terms, first the science and then the implementation. So for the first talk, Nuria Calvert from University of Michigan, why is the UV important for young, low-mass, cool stars? So.
Okay. Yes. Thank you very much. First of all, yeah, I want to actually thank the organizers for inviting me to give the talk. And maybe I should, can you see there? It should be on. If you can hear me. How about that? Can you hear me? No? Yes? Good? Okay. Yeah, I'll try to speak. Can you put the timer, please? Thank you. Right. So I want to thank the organizers for inviting me to give this talk. And I would like to start with a kind of probably distorted history here, a little bit of history, but kind of distorted. The idea, like around 2019, Ken Sembach, that was the director of HST, decided to give around 600, 1,000 orbits of HST to star formation, right? And then a UV legacy working group was established, and Sally Hui, who was the chair of the group, she thought that maybe it was a little bit unbalanced because at that point it only had like one person in low mass stars, and so she actually invited two low mass young stars people working on that, Greg Herzeg and myself, and then just to get the balance a little bit better. And so, and then we worked pretty hard preparing the report, and eventually, so I don't know how, now it's not working. So that's, Ulysses was born, and then, okay, I guess it doesn't work. Ulysses was born, and after a lot of effort, we had a nice report. 1,000 DDT HST orbits were dedicated to star formation, thanks Dr. Sembach. But for us, it was very important because 500, half of those were dedicated to low mass young stars, and the low mass stars community is very thankful to Sally Hui, who must be online, and I told her to be that. Okay, so, but now I will address my topic, which is why, just to show to you why the UV is important for cool stars. And the thing is, and I think that there is in many of these communities, low mass stars, aren't they like too cold to emit in the UV? Anything important? Okay, I'll show you. I'll talk about this in this talk. But first, just to give you an overview of star formation, we start with this molecular cloud core that collapses when it loses pressure support. And then we have like eventually a star is formed because of angular momentum. The star is formed surrounded by a disk. The disk accretes onto the star. And eventually, sorry, in this, your favorite. So sorry, I don't know how to handle this. Okay, so a star is born surrounded by a disk. In that disk, planets form, and eventually the disk evaporates, and only the planets are left. Now, the phase that I am concentrating is more like this, right? Because that's the phase where the envelope is gone, and then the UV can be seen. So the main thing, the main story is this. This is the iconic Lee Harman's figure, the figure that we use in all our collaborations, but now it's enhanced. It's got a chromosphere, even it's got a planet. So, but the main idea is that you have a disk. The disk is actually accreting mass onto the star. It's accreting mass onto the star, right? And then at some point, when for typical mass accretion rates of 10 to the minus 8 and typical strength of magnetic fields of 3 kilogauss, then the magnetic field disrupts the disk, and matter falls onto the disk along magnetic field lines, right? And of course, it's free fall, so when it crashes into the photosphere, at 100 kilometers per second, and it merges into the photosphere through an accretion shock. Now, in the stellar surface. So what happens is that this accretion shock will emit in the optical, in the UV, and line and continuum emission, some X-rays too. Like in these magnetospheric flows, you will form like the very broad emission lines that characterize Titori stars. And in addition to all of that, of course, this star is magnetically active. So it's got a chromosphere, it's got a corona that emits in X-rays and a little bit of UV. And the other thing is that at some point, this disk that actually is heated by viscous dissipation, but also by radiation of the star, I'll show you, then it actually, so all the dust sublimates, and you have like in a gas disk. Okay, so that's the general picture, and I'll show you then like the details. The main thing is that you have like this accretion shock on the surface up there, right? And then what's going to happen is that you have like a shock, right? This matter, I think I have a pointer here if you don't mind. Sorry, I think that mine works. Okay, so, yeah, so, okay, so you have like this a shock in here, right? And matter is falling into, matter is falling and then it crashes, forms a shock. The shock emits in the X-rays, soft X-rays, hit like the pre-shock, hit the photosphere below it, it reprocesses radiation and everything comes out. And it comes out in, mostly in here, right, is as an excess luminosity over the stellar photosphere. This excess luminosity is mostly in the UV, and therefore is only accessible through HST. So why is this important? It is important because, you see, when you have this excess emission, this emission is identifying accretion, right? Where does this energy come from? That energy does not come from stellar activity, right? This is too much to come just from stellar magnetic activity in the stars as inactive stars. This can be of the order even of the stellar luminosity, sometimes even more. So it has to be potential energy, gravitational potential energy released as the matter comes in. So, and so it identifies accretion and then provides a measurement, a good measurement of the accretion luminosity, that excess luminosity, which is just potential energy. But the very important thing is that it provides mass accretion rate. And the mass accretion rate is through the disk onto the star, right? So you have then a direct connection, with, direct connection of the UV with the disk. The UV is directly connected to physics in the protoplanetary disk. And so, for instance, because the UV has this excess luminosity and has this accretion luminosity, you have accretion, right? Accretion in the it illuminates the surface of the disk, heats it up, hits the disk, and then determines the gas temperature in there, because it's mostly photoelectric effect, and also because photodissociation, ionization of molecules and atoms in there. And this is very important because this is the site of molecular emission that we see in JWST and ALMA, right? So that's very important. The next thing is that continuing with this UV disconnection, the accretion luminosity determines the location of this site. This site is very important. We call it the dust wall because it does look like a wall if you want to. This is a pretty picture from Belerique, Luis. And the idea in there is that, of course, the temperature in the disk is determined by how much energy is accreting from, absorbing from the star. And if you had extra luminosity coming from accretion, then it can be further out, right? So this location, and that's important because this is essentially like the near infrared, that part that is probed by JWST, comes essentially from this region, this dust wall, the dust destruction radius. Right? Another important implication of this is that, punchline. So the idea is that it determines, as I said, the location of the dust destruction radius, and that's very important because it can be this sublimation, or it's a snow line, but of course of refractory material, can be like a dust trap for pebbles, planetesimals you can accumulate there, and that corresponds, interestingly, with the location of these tightly packed inner planets, that Earth and super Earth, which are like the most frequent, abundant of type of planets. So the study of this region is very important. Another thing is that, of course, M dot is a fundamental constraint to planet formation population synthesis because, like, this is a study by Carlo and collaborators. An idea is to compare models with observations, models of observations of mass accretion rate with the mass of the disk, and these are the different models. These are some observations, but when you see models of the giant planets, what you see is that they tend to fall into this region. This is like PDS 70, which is the planet, right? The one that we have H alpha, that we have little disks around that. It's the only one so far that's so complete, but we hope to get more. But the idea is that we can put a very important constraint on the origin of this type of systems, just because by measuring the mass accretion rate onto the star for comparison with model predictions. Another thing is that magnetospheric accretion like this, again, UV disconnection, again, we provide M dot. Well, it provides like a local heating of the disk, because the fact that we have accretion means that we have some viscous dissipation that heats this region, the innermost region behind the dust wall. And this is the type of formation of chondrite material, for instance, in the solar system, and we think in other objects, right? So that's an important thing. It's also, M dot is also an indicator of the disk surface density, right? Which is, if the disk is steady, for instance, is something like that. And this is an important thing because it's a constraint from planets forming and everything that's happening in the disk, right? So, and another thing is interesting is that it says when photoevaporation sets in, because the idea very simplistically is that as times the disk ages, the mass accretion rate decreases, the mass of the disk increases because it is dumped into the star. And at some point, if you have this photoevaporation like this, the surface layers are photoevaporating because they get to velocities that are higher than the escape velocity. Then when this m dot in equals m dot out, then the star doesn't receive a mass accretion rate anymore. The disk opens up and eventually photoevaporates. So it's one of the termination of the disk. So that's an important constraint too. Then finally, there is the FUV disk connection. The point here is that when we look at the FUV, we see all these lines, and I put just this low resolution spectra because you can see better, but of course there's more beautiful things like this. These H2 lines, and the point here is that you have, if you look at the H2 molecule, that is the most abundant molecule in the disk, but it's the most difficult to see, right? But this one, the idea is that you have Lyman alpha at 1215, and Lyman alpha can excite the H2 molecule from the ground state to excited electronic states. And when it goes back to the de-excite to the ground state, then it produces this plethora of H2 lines, right? And that give us direct view of the inner gas disk. Like for instance, this is like a much better data here, right? You can see like the different H2 lines in comparison with a star that does not have accretion, a Witty-Torres star. You can see they are not present. And when you actually see them with the high resolution of cost, what you see is that the breadth of the line, which can be measured, is consistent with velocities of the inner disk, right? So that gives us a view of that. In addition, when we have Lyman alpha, one very important thing, and you'll hear more about it, is that we can reconstruct Lyman alpha. When we have like these H2 lines, we can reconstruct the Lyman alpha profile, right? The Lyman alpha is absorbed badly by H2, by neutral hydrogen in the field, right? And so we hardly see anything. But we can reconstruct it, because if we look at all the H2 lines, they come from different parts of the profile, right? And so this is a beautiful work done started with Greg Herzeg and is continuing, and you'll see some more of this in this conference, right? So you can reconstruct it. And why is this important? Well, it's important, again, for the disconnection, right? The thing is that when you look, especially now with JWST, that we have, or an ALMA, that we have all this molecular emission, hateful molecular emission, but it's so important, right? The thing is that when you look at the channels for photodissociation, photoionization, right? So you can calculate the molecular dissociation, which is the cross sections times the intensity, right? And when you look at the cross sections of the different molecules, what you see, they are mostly in the FUV or a little below, and then you see whether or not H alpha affects it, right? Because, for instance, when you look at this, an example that we did back in 2003, HCN and CN. HCN does have Lyman alpha falls into the region where HCN can absorb radiation. CN, no, I put it far away, right? And so what happens is that the resulting dissociation rate is very different, right? So depending on how much Lyman alpha you have, like the different molecules are going to be dissociated differently, differentially, and then that affects, of course, the spectrum that we see. And you can see that this is very important for the spectra that we are seeing now, because water, for instance, and even methane, they have Lyman alpha in the field. They can be affected by Lyman alpha, CO no, right? And so this is fundamental, and I don't think it has been taken enough into account, but because it's very important for the proper interpretation of JWS spectra, right? So it's not just LTE, you have to take that because photodissociation is fundamental. It comes from the surface of the disk, and that's going to be affected by that. Okay, so, and of course, these rates have to be calculated again. We have cross-section, but we have to take into account the proper spectrum, and of course, it has all these hot lines, right, that come from the accretion shock, and that could have different implications, impact on the rates. So finally, Ulysses, this is like the low mass counterpart, right? These are like the co-spectra, the FUV that are important for Lyman alpha, this chemistry, the NUV that was observed with STIS, important for mass accretion rate. And one important thing is that we have simultaneous measurements of the mass accretion rate and emission lines of a very large wavelength range. Even though it's low resolution, but we have that. And we have like Ulysses went over 72 targets of different ages. That's very important too, because they essentially cover the range in which this disappears, right? Except for the low, the old disks, there is something missing here, but maybe in the next proposal we can solve this deficit here. I'm advertising it, yes. So yes, but because it's very striking, right? It's beautiful, like, and there are targets. Okay, so summary then, I'm almost there. So why is the UV important? Well, it's important because young, low mass stars are surrounded by disks and are accreting mass from those disks, and then they are releasing energy. And this energy is released mostly in the UV. So we have this connection between the disk physics, which we are all interested in because we are looking for planets and how planets form, this connection with the UV emission. So we have this. So UV is directly related to this accretion phenomena because accretion is the source of energy for the UV emission. So then from the UV, we get accretion, luminosity, mass accretion rate. That is important for the temperature, the surface density, the inner edge of the disk, the onset of photoevaporation, molecular dissociation, and also the ionization structure of the disk, right? Which is also important for MRIs and all mechanisms of dealing with the creature. And finally, there is plenty of science to do with that. But also, one important thing of Ulysses for our community was these offsprings, these Odysseus and Penelope that you'll hear in the next days. These are the largest collaboration of researchers in low mass young stars that there ever been. I mean, I never seen that, and I've been in this business for a long time, but I never seen the collaboration, maybe not so much that, but there is still, right? The collaboration among people from the US, Europe, Asia, from so many places in the world. It's been absolutely wonderful and continues being. The many papers so far, several PhD theses, but it's also the beginning, as it was said before us, because there is a lot of science to be extracted with the data, right? And it keeps coming. So much more with this treasure, this invaluable resource, is a HST legacy treasure. And so, thanks.
Okay, thank you. Let's start with in the room and then alternate online. Question there? Yes.
Sally Heap, Goddard Emerita. Thank you very much for such a nice physical explanation about low mass formation of low mass stars. And it got me to wondering, why don't we have such a picture for high mass star formation? Does this general picture break down, or is it just missing observational evidence? And if it does break down, why? Where does it break down?
Well, I think that it's in part a question of timescales, right? Because low mass stars, when they actually appear, they order them in sequence, right? Because they live so shortly. There are observations of some disks around young stars, but those are because of the nature of the beasts. They are located in very, very heavily embedded regions, so it's very hard to get into them, right? But some have discovered and some have jets. I don't know so much like the OB stars that you people deal with, but like the B0s and late O's, some have been discovered. The other thing is that it's the magnetic fields. These our objects have like this because of the convection. So they do have strong magnetic fields, magnetic activity, and I don't think it is as important in the higher mass stars. And so you don't have like this magnetospheric accretion, I think. But I know nothing about high mass stars.
We have one more question here.
Thank you very much for a nice overview. I just actually two very small questions in the details. And the first was, you talked convincingly about the effects from the heating of the material that is falling back on the photosphere of these T-Tower stars, and that you saw on UV excess, right? Is this also seen, but then you showed in the optical, so to say, it sort of vanished from the pure photospheric. I was just wondering, is there a difference also in that part? I can imagine when you have accretion and then you shocks up, that the ionization balance actually would also be switched in the optical, so that your photosphere would look hotter than in a normal. Is this something that you have seen, or yeah?
Well, you
exactly,
see,
yeah.
You see more.
That exactly, yeah.
Kelly Pinman, she will show more of the results of this. But essentially, what happens is, if you look at here, You can think of it like you have the photosphere, but then like the emitting region of the shock or especially the shock is so small, right? So in principle, you can actually add them up.
Okay.
And so what you see is that I did say that you have like this excess here, right? But you can see there is excess also a longer wavelength, and even a longer wavelength. And in fact, so we do like complicated, well, a little bit more complicated than a single column like that, several columns with different energies, with different fluxes. But essentially, the effects on the photosphere, right, the heated photosphere, yes, probably they are distorted, the features, but they don't seem to be as important as like the veiling, the veiling that is due to this extra emission.
I see. Yeah, thank you. And then just a very small, when you talk about the accretion rate and you connect it to the luminosity, is the efficiency factor there in this field when you do it important, or can you do a direct link between the luminosity and the accretion rate? Or do you always have to assume some sort of efficiency, accretion efficiency, which I know in other fields is very important?
Yeah,
right?
yeah, of course. Well, first, the main thing here is where the efficiency, meaning that from the luminosity we measure, let me see, from the luminosity we measure is from where, here. From where the material is falling, right? Because the luminosity is not just accretion luminosity, as I say, G, M, M dot R. There is a factor in here that depends where it falls. Now, for typical truncation radius in here, which are 3 to 5, like 80%, or roughly 80% of the luminosity, the excess luminosity we measure is accretion luminosity. This factor is just like decreases, like, yeah, right. So within the errors, I don't think you can do much better than that. But we are trying to make a consistent models of the flows with excess luminosity and the lines that do in here that come from this here to see if we can do a more consistent. The thing is that you can push consistency to several extent, because in fact, these objects, nothing is axially symmetric and beautiful. I mean, the numerical simulations say this is much more complicated than that. So we do the best we can. Sure.
So let's thank Nuria again, and then have our next speaker.
Thank you. Oops, sorry. You want me to take?
Oh, yes, sure.
This is working.
Shall I use the Does this work? No, the keynote. Yeah.
Let's use this one.
This one. Yeah.
This goes to the next slide.
Okay. Let's go to the first, yeah.
So the top one is this is the pointer.
Yeah. Okay.
All right, so second talk this morning, Jorik Wing from Armagh Observatory, talking on massive stars and Ulysses, LOSI. Take it away, Jorik.
Yeah, thank you very much.
The timer's going to be here.
Yes. So, well, first of all, I want to thank the director for making this all happening, and then Sally Oy and the working group team, and then Julia and the implementation team here for organizing Ulysses and this workshop. So, thanks very much. For me, it's quite special to be back here. I've just realized that the first time I was here at Space Telescope, I was a master's student at Goddard, working with Sally Heap, and Sally is in the audience, so that's very special for me. Okay, so see, everything that is interesting happens in the same environment. So Tory stars as well as massive stars happen in the same environments. Mostly Tory stars form near massive stars. So if you want to understand the Tory stars, yes? Is now better? Yeah, okay. So you need to understand massive stars to understand Vittori stars, in many cases, at least. Okay, so why are massive stars at low metallicity interesting? Then I'll talk about the need for UV large samples, but also the need for more theory so that we can use the spectra to test these theories. So this is a plot I made a couple of years ago for an overview of a volume I was editing about star formation in the ultraviolet. And as you can see, the hydrogen-rich universe has, so this is basically the HRD for stars between 1 and 10 million years. So we have the Vittori stars we just heard about. And then the O stars are above the birth line, so all the action is not really not ideal. But anyway, you have the O stars here. We don't see their primitive sequence. Yeah? They have already appeared. The moment they appear from the dust, they are already burning hydrogen. So maybe the Herbig stars can teach us a lot about what happens between the magnetosphere accretion here and presumed radiation pressure disk accretion in the O-type stars. I would also like to say, a lot of people think O, B, A, F. That's not true. The earliest type stars are not O-type. They are W and H. They probably already appear for the first time as Wolf-Rayet stars with a lot of hydrogen in the spectrum. So stars over 100 solar masses are not O-type, but they are very massive stars. And they're very relevant for high redshift. Really working very well, but the other part is the helium-rich universe. These stars, when they lose a lot of mass in winds, they become classical Wolf-Rayet stars. Or they lose their envelope via some other mechanism, like a binary interaction. But if a galaxy like the LMC has hundreds of Wolf-Rayet stars, we should have thousands and thousands of these stripped helium stars below this, if this was an important channel. But we now know they exist. So that's great, but not in their thousands, but in their tens. So there's a lot of, we still need to understand a lot about stripping stars before we can understand things like supernovae and black holes. Okay, so as I said, if you want overviews of these things, I can refer you to these chapters by people, some of them in the audience. There's also for the O stars, when we go up the mass range, for the O stars, spectroscopy by John Hillier, and then we go to higher and higher redshift, first locally and then high redshift population synthesis. We need to understand the spectra of massive stars, both the O stars and the Wolf-Rayet stars, to make better population synthesis models and to understand things that happen at redshift 10. So, why massive stars at low metallicity? First of all, we need to understand how mechanical feedback changes. Mechanical feedback is mostly set by the wind velocity, which you can only get from the UV. The ionizing feedback that is provided to galaxies largely comes from hot massive stars. So we need to understand that, well, we talked about photoevaporation of disks for Vittori stars. It can happen, of course, locally, but those disks can also be photoevaporated by nearby massive stars in some cases. And then there is the issue of the cosmic reionization. After a couple of 100 million years, you had the first stars forming, and one of the prime candidates is massive and very massive stars doing the reionization of the universe. And we need to really understand the whole chemical and ionization history of the universe. And we are sitting in a big galaxy like the Milky Way here at solar metallicity with lots of Vittori stars around us. But if we want to learn something about our history, the very first stars, one thing we can do is look at JWST and look at redshift 10 galaxies. But that's all integrated light. If we want to understand the physics of the individual O stars, we need to look nearby. And fortunately, there are a couple of dwarf galaxies at lower metallicity, like the LMC and the SMC, at 50 and 20% solar, that we can study with Ulysses. Now, the ionizing flux is strongly dependent on the mass loss rate, especially the helium-2 ionizing flux. So if you have mass or luminosity going that way, and the mass loss rate over here, then you can see the red line gives you the mass loss rate. And if you now look at the ionizing flux on this axis, the helium-2 ionizing flux can be quite significant for optically thin winds. But once you reach a critical mass loss rate, the helium-2 ionizing flux gets completely blocked. So if you have your mass loss rate wrong, and I'm not talking about a big effect, this is a tiny change in the mass loss rate, your helium-2 ionizing flux, it doesn't change by a factor 2 or an order of magnitude or something like that, but by thousands. So understanding the winds is absolutely critical for understanding helium-2 ionizing radiation. And the hydrogen ionization, less so dependent on the mass loss rate, but it's strongly dependent on the temperature. The temperature, I'll show you, is strongly dependent on the mass loss rate. So again, we need to understand the mass loss rate. And also for the chemical arrangement of the universe, both in winds and supernovae, we need to understand the mass loss rate. So if we look at high redshift galaxies, and this is now in the JWST data, what is found is that there is enormous amounts of nitrogen at high redshift with nitrogen over oxygen, which is supersolar, and no one understands. And there are a couple of suggestions for this. People have suggested rotating Wolf-Rayet stars. That's an interesting suggestion, but we haven't really found rotating Wolf-Rayet stars yet. Then there's a suggestion of supermassive stars, 10 to the 4 solar mass stars. Also very interesting, but again, we don't know if they exist. Now, my own suggestion is very massive stars, because we know they exist, and we know that they produce, 200 solar mass star produce a solar mass of nitrogen. That is a really significant amount. Now, independent of any, my preference, of course, is the very massive stars, but for all of them, we would need to know how the winds change with the metallicity. That is absolutely key for understanding the chemical enrichment of these high redshift galaxies. And again, the winds set the evolution of the star. So you start having a mass loss rate, and you start removing the hydrogen envelope, and at some point you start to make a black hole, but all that depends on the mass loss rate as a function of metallicity. And this is particularly interesting with respect to LIGO detections of black hole, merging black holes. They are actually at masses now, 66 and 85 solar mass, black holes have been detected. And these are above the traditional pair instability supernova. So you have a mass gap between neutron stars and black holes. Then you have an upper mass gap above 50 solar masses, where the star is completely blown to pieces. So a 300 solar mass star could be blown to pieces in a pair instability supernova, producing 300 of solar masses of metals. So knowing if that happens or not is absolutely critical. But all that will depend on metallicity. So we did a study a few years ago because of this very interesting 85 solar mass black hole. And if you plot the maximum black hole mass versus metallicity, low metallicity to the present day with high metallicity, we increased the pair instability limit by almost a factor 2 to 93 solar masses. And then at high metallicity, we expect very strong line-driven winds, give you black hole masses of at most 20 solar masses. Now, but there's a transition happening somewhere. You get the very onset of the winds. We place this at about 1/10 solar, but it's highly uncertain. It all depends on the absolute mass loss rates. So again, we need to understand the absolute mass loss rates to understand the black hole mass function. Already 20 years ago, people found these, this is a composite of like 1,000 Lyman break galaxies of redshift 3. They found these very interesting helium-2 lines. So you have carbon-4, typical stellar winds from massive stars, but there's also this broad helium-2 emission, which was not understood at all. The narrow lines are normally explained as ionizing flux, but the broad lines are usually thought to be stellar winds. But none of the stellar population synthesis models at the time could reproduce this. And it doesn't really matter which one you used at that point, because very massive stars were not included. So again, in order to understand these kind of features, you need to understand very massive stars, and you need to understand their winds. And if we now look at normal O stars, they have these carbon-4 lines, but their helium-2 emission is basically not existent. And only if you go to very massive stars, actually slash stars, then you start to see this transition from nothing present to very strong helium-2 emission. And this is why I keep saying that the very massive stars need to be included in these things. So what do we need? We need mass loss rates as a function of metallicity, luminosity, mass, effective temperature. Yeah? That means we need an m dot and v infinity, the properties of the wind. Yeah? But in order to compare theory to observation, it isn't just a matter of knowing the mass loss rate, you also need to know the underlying stellar parameters. And that's the only way you can make a comparison. Yeah? And again, for that you need both optical and UV spectroscopy. So this is what we need. And in order to do anything meaningful, if you have so many different parameters, yeah, if you want 5 luminosities, 5 masses and 5 temperatures, yeah, you want 5 times 5 times 5, that's already 125 stars. Yeah, so that is kind of where the Ulysses sample comes in. So for 2 metallicities at least, the LMC and the SMC, it is feasible to have a bit of a range of masses, luminosities and temperatures. And that is then translated into luminosity classes, and we'll hear about that more later. So, what you really want to do is combine optical with UV. So in the UV, we get terminal velocities from the blue edge of P Cygni lines, like carbon 4. Yeah. We can get iron abundances from the iron forest, and then from the optical, we can get temperatures, gravities, and also we get a handle on the mass loss rate from H alpha. Now, up to Ulysses, large samples were only done in optical, yeah? Like with the VLT flame survey, and we had all these nice H alpha mass loss rates, but they depend on clumping. So we don't know how much of this is due to mass loss and how much of it is due to the physics of the clumps in the wind. To disentangle these effects, and especially effects of micro and macro clumping, I won't bore you with the details, let that over to other people later on, but by having the mass loss rates in the optical and from the UV, you can potentially at least disentangle these effects and actually get the real mass loss rate of massive stars. But that is why Ulysses was born. That is the physical reason. Of course, we also, for these population synthesis models, need libraries to really see what is the UV spectrum. When you redshift that into larger redshifts, what kind of spectra do you expect? That's the second big driver. So these are the samples. LMC and the SMC. As you can see, there's lots of O stars, B stars, and these, both Wolf-Rayet stars and these slash stars, which are basically very massive stars. And you see them spread out in the LMC and the SMC. If you look at them in the Hertzsprung-Russell diagram, and these are pre-Ulysses temperatures and luminosity, so they can change. This is thanks to Paul Crowder and Alex Fullerton. Already make preliminary HRDs, so at least we got an idea of the sample that we have, and we can see that for the LMC, we have stars quite nicely populated up to quite high masses here. For the SMC, the most massive stars don't exist, but still they are up to quite high masses. And we can really start to compare stellar evolution and stellar winds in 2 environments. In my mind, the LMC at half solar, in terms of its physics, is quite similar to that in the Milky Way. Whereas in the SMC, which is 20% solar, you now really have a reduction in your mass loss rates, so that the stellar evolution becomes really fundamentally different. So this is much more characteristic of the early universe, at a redshift of 3 or so. Okay, that is why we need Ulysses. Some early science already, some papers, mass loss rates versus luminosities by the Amsterdam group, and what is found is, at least from these early results, is that not only are the SMC mass loss rate lower than the LMC rates, but actually the slope seems to be steeper. So the mass loss rate versus luminosity seems to have a steeper slope than in the galaxy. So that is quite interesting, but we need further models and further data to confirm this. These are still relatively small samples and still not anywhere near enough for the entire sample. Then also testing mixing in massive stars. Is a nitrogen abundance versus log G. So stars evolve from high gravity to low gravity. So this is kind of an H axis, and this is like a mixing efficiency axis. And what you see is in the SMC, there's more nitrogen enhancement than in the higher metallicity ranges, and suggestive that indeed at lower metallicity we have more efficient rotational mixing. But again, these are small samples, it's preliminary. We need much more work to confirm these findings. As I said, one thing is to get the data, the other thing is to understand it. And to me, these things go hand in hand. You need to understand the physics underlying the models and at the same time look at the data. And I think there's a lot of progress going to be made over the next couple of years by comparing the two. The theory is that of the line-driven winds, developed by Castellan and Klein, and the main element driving the winds is iron. So in reality, in our models, we include all the other elements like CNO, silicon, etc. But iron has millions of lines, so that is the main driver that sets the mass loss rate. That is why we keep talking about the iron atom. And in reality, this is a multiple scattering process. So the single scattering in the previous slide isn't the full story. You need to include multiple scattering. You can do that in many ways. I do this in Monte Carlo. Other people use co-moving frame approaches. And they give somewhat different results. Our mass loss rates are generally slightly higher, a couple of factor 2 to 3 higher. And these are things we still need to investigate. But the mass loss rate, V infinity, can exceed L over C. What does that mean? The momentum in the radiation field, L over C, if you have a very efficient multiple scattering process, you can actually exceed that. And that is what happens for these very massive stars. So in the last few years, we have now implemented what I call the wind kink. If you plot the mass loss rates of normal O stars, they are in what I call the low gamma regime. So these are normal O stars. And we can argue about the absolute values. But the other important effect is that mostly people have extrapolated these kind of relations into the regime of very massive stars. But what you really need to do is that when you cross a certain wind optical depth, you have a boost in the mass loss rate. And we calculate that boost now so that we can actually include the correct enhanced mass loss rates, or we think to be the correct enhanced mass loss rates of very massive stars. And it resolves a number of very important properties, I think, of very massive stars. So if we include this in stellar models, this is with MESA, if you have an HRD for very massive stars, so this is a low mass 100 solar mass star, if you reach 100 solar masses, you're already quite close to the Eddington limit. The star wants to expand, but it also wants to inflate because of its proximity to the Eddington limit. If your mass loss rate is not existent, the star wants to actually inflate like crazy. It becomes a red supergiant very quickly. If the mass loss rate is too high, the star wants to become a classical Wolf-Rayet star. To get that balance right between the inflation and the mass loss, which are both an effect of gamma, is extremely tricky. So even if you came up with a mass loss recipe that gave you the right behavior at 100 solar masses, then to have that same recipe doing 101 solar masses is almost impossible, I would argue. Because you add 1 solar mass and the thing again will inflate like crazy. So it is a very delicate balance between inflation and mass loss. And in my mind, the only way to explain the fact that actually the temperatures that we observe are never in the red, the Humphreys-Davidson limit, and they're never in the blue, but they're always around here, means that the mass loss rates have to be really high so that the stars evolve vertically downwards. This is what we call vertical evolution. It really doesn't matter whether you start with a 500, 400, 300, or 200 solar mass star. They all quickly become very massive stars, all at about the same temperature. And this self-regulatory effect is, I think, the key aspect of what we see in these spectra at high redshift. So the spectroscopic transition is that when you have the helium-2 line, in the optical in this case, you go from absorption lines to weak emission lines and then to very strong emission lines, and that is all a function of the mass loss rate. And the same will happen in the UV at 1640. So that is probably what we see in the integrated light. Here's R136 in the LMC. As you can see, there is this strong helium-2 line, because the O stars, the normal O stars, there are 10 times more normal O stars than there are very massive stars, but the normal O stars have no helium-2 emission, and the very massive stars, the 7 of them, produce all of it. So again, just understanding the carbon-4 is not enough. We really need to understand that helium-2 line, the very massive stars. Now, finally, I wanted to also mention that in the extragalactic community, when people see narrow helium-2 lines, like was the case here at the redshift 7, people immediately say, okay, this is ionizing radiation, that means the star is very hot, probably population 3 star, very hot star. However, it is maybe not the only possibility, because what we haven't considered is that the broad helium-2 lines from stellar winds could be narrower and narrower when the properties of the stars change, in particular the metallicity. And this is what we did a few years ago. Here we have the high metallicity case, a tenth and a hundredth. And if you now look at the helium-2 line again, this is quite broad, more than 1,000 kilometers per second. But then when you go to lower and lower metallicity, these lines become narrower and narrower. So we really need to understand the wind physics as a function of metallicity to understand whether the narrow emission is nebular or stellar. That was as a function of metallicity, but there are other factors that set the wind velocity. And one of them is the temperature of the star. Now, if you plot the V infinity that you can measure from the UV versus effective temperatures, then there seems to be, at least in my predictions, a very strong drop in the wind velocity at 20,000 Kelvin. And that coincides with a strong predicted increase by a factor 5 or so in the mass loss rate. And this has been confirmed by other models, CMF-Gen models of Petrov, Krtichka, but other predictions by Björklund et al. Find no such jump. So something like, it sounds like this is maybe a detail of wind physics, but this is really important to know if this is true or not, because stars at the bistability jump at this temperature of 22,000, they might be rare. Maybe only 10% of stars is sitting there right now, but all massive stars are supposed to, when they expand, to hit this temperature regime. So knowing whether their mass loss rate changes and their wind velocities change is quite important if you want to understand black holes and so at the end. So there's a lot of physics we need to understand. And for all that understanding of the wind physics, we need to understand the spectra of Ulysses. So the spectral libraries are critical for star-forming galaxies. UV is absolutely critical for understanding the wind velocity as well as the mass loss rate. And you really need both, because from the optical we get things like gravities that are more sensitive to the Balmer lines than to lines in the UV. And as I said, we need, in tandem with the observational efforts, we need more theoretical development to understand the mass loss rates. And if you understand the mass loss rate, you might understand the ionizing fluxes, but also you need to understand the evolution. And for that, you need a large team of people. And that is why I see this whole project not only as an exercise in obtaining the data, but also in working together as a community to get better understanding of the winds and the evolution of these stars. And I refer to Frank Tamper later on to talk about the X-shooting Ulysses collaboration. That is open for everyone. Okay, thank you.
Thank you. Let's see, this time if we have a question online, let's start there. Anyone in the room? We have time for a couple of questions.
You mentioned the importance of sort of characterizing the structure of the winds and the clumpiness in particular. I was wondering if you have any comments about using linear polarization to perhaps like better characterize the winds and their structure, and whether that would be useful in this case.
Yeah, that's actually one of the things I like very much. Exactly. We now have two mechanisms for producing structure in stellar winds. We'll hear more from John Sundquist. One is in the wind, slightly shadowing instability. People have talked about that a lot, especially for producing X-rays in O-star winds. But there's also subsurface convection zone induced by iron, and that causes all kinds of turbulence and funny effects. And the polarization of LBVs, a study we did with Ben Davies in 2007, suggests that there has to be already structure very deep in the wind because of the line polarization effect. So we now will hear more about this, but I think it's becoming more and more clear that the structure doesn't start with the LDI, the structure really starts in the photosphere. And I think line polarization will be very, very useful, especially monitoring will help you, will both constrain the sizes of the clumps and the location where the clumps appear.
For one or two more questions, anyone online?
Jorik, one question about your very interesting paper you had with Götz Grafner a few years ago about the narrow helium-2 1640. Earlier in your talk, you showed how the helium-2 emission from stars is very sensitive to the mass loss rate. But then at the same time, it would also be sensitive to the velocity via the density. So would you expect that the helium-2 emission would then be also reduced because of the lower velocities and therefore higher density, so that you would also have recombination in the wind and the effect would disappear?
Oh, sorry, yeah, quite possibly. I think the narrow lines, if that is the ionizing radiation, I think will be highly sensitive to the mass loss rate. Really, if you change it by a tiny bit, you suddenly go off a cliff. The whole thing becomes optically thick. Not a single photon comes through. To produce those stellar lines, that will be slightly less sensitive.
So if there's no more last questions, let's thank Jorik again. After these two talks that have given a beautiful overview of the scientific motivation for Ulysses, we have 3 talks on design and implementation, and we'll take questions after those 3. So Julia, start off.
Yeah, so it's really one talk, but Alex Fullerton, who is the technical implementation lead for the massive stars and also our lead expert on massive stars, and then Will Fisher, who's the technical implementation lead for the low mass stars and lead expert on low mass stars, will join me for this talk. If I can first open it. Let's see. This one. There we go. Okay, got it. Thanks. All right. Yeah, so the SOC thought that it would be probably helpful for us to share with you our thinking in implementing this very large program, the scientific decisions that we had to make along the way in order to turn this UV legacy report that Noria mentioned into an actual program with a set of targets, telescope files, and data products. And so that's the goal for this talk. And as I said, Alex Fullerton will cover the massive star observing part as well as initial results, and Will Fisher will do the same for the low mass stars. I get this question a lot, right? How did Ulysses came to be? First of all, I want to say Ulysses is an acronym with actually a spelling mistake. So it's the Ultraviolet Legacy Library of Young Stars and Essential Standards. As Jennifer Lutz mentioned, it is the largest HST program ever executed with 1,000 orbits. And really, it was a program that was designed by the community for the community. And so initially, I guess Ken Sambar consulted with the science staff at STSEI to try to decide what kind of large DD program should we do. And the idea got settled to do something focused on young stars and star formation. And so at that point, the whole project was handed off to a UV legacy working group composed of external community experts on low and high mass stars. And they produced this very nice report that really outlined the science goals and the observing strategy at a high level of the Ulysses program. And of course, as we know now, thanks to these wonderful introductions for the 2 components of Ulysses, low and high mass stars, 500 orbits were dedicated to extending the spectroscopic library of O and B stars to lower metallicity than the Milky Way. And 500 orbits were dedicated to UV spectroscopy of T Tauri stars, so younger than 10 megayears, with a focus on the lower mass stars, so half a solar mass or lower. So in a nutshell, on our side of the implementation, this is what Ulysses was. The observations were completed last July in 2023. It amounted to 986 orbits, 2,252 exposures, 220 targets, and 86 phase 2s. So far, we've had 8 data releases. The first DR was in November 2020, and our last DR was recently, a few months ago in December 2023. And that it pretty much included everything that we wanted to release to the community in terms of data products and tools. So before I get to the details of the implementation, I wanted to give a shout out to the implementation team, the Ulysses implementation team at STSEI. So I don't know if there's any of you in the room, if you can stand up, because I think this was a heroic effort, and I really want to give them a shout out. Thank you, guys. We were also helped by an external science advisory committee of experts on low and high mass stars that really helped us make the decisions that we had to take in order to really turn the report into an actual observing program. So these are Jean-Claude Bourret, Catherine Espayet, Chris Evans, Kevin France, Miriam Garcia, who's here, Chris Jones-Squills, Dirk Massa, and Joanne Najita. And they were extremely helpful, especially in the first couple of years of the implementation, into helping us out to make the right decision and optimize the program to achieve its goals. Okay, so science goals. I'm not going to dwell on this too much because we had a really good, extensive summary of those goals from Noria and Joik. So for the massive stars, as you just heard, right, the goal was to create this very complete spectral library that would allow the community to characterize the wind properties of massive stars, their mass loss rates, their ionizing radiation, all that as a function of metallicity, temperature, and luminosity class. And then ultimately, those spectra also provide the spectral templates that are necessary for population synthesis and understand the earliest stars in the universe. But I do want to point out that this component of Ulysses actually touches many more fields of astrophysics, and in particular, the circumgalactic medium and the interstellar medium. Why? Because, for example, for the circumgalactic medium, those spectra towards O and B stars have the imprint of the CGM in them, and so you can derive some kinematics, metallicity, and even study the disk-Heller interface and feedback. For the ISM, you have a lot of neutral gas absorption lines that are intervening between the star and us. And you can derive chemical abundances from those, as well as dust depletions, which is very important to understand the cosmic buildup of dust, not just in the nearby universe, but at all redshifts in general. Okay. Ooh, no, too fast. No. What? I want to go backward. Sorry. This is a little... Maybe because the figure's too big. Yeah, okay. Science goals for the low mass stars. So Noria, of course, summarized this really nicely. But the goal here is really to understand accretion physics in those low mass stars, and actually in other types of compact objects, and understand all the diagnostics of accretion physics. Ulysses also designed to understand the UV radiation coming out of those still forming low mass stars, their impact on the disk chemistry and evolution and dispersal, as well as planet habitability and atmospheric escape. There is a time monitoring component to the low mass star observations in Ulysses that is 100 orbits. And with that, we monitored 4 prototypical T-Tauri stars over time, and I'll get into more details on how that was done. But the goal of this was really to study the variability of accretion in those T-Tauri stars. And on the right here, you can see an example of a single epoch spectrum towards one of the Orion stars that we observed, going from the FUV all the way to the infrared, the near infrared. And then at the bottom here, you can see why it's important to monitor these stars over time, because a lot of the variability happens in the UV. All right, so I think this is probably what you're going to be most interested in, is how did we select the targets? It was a long process. So we followed the same strategy for both components, low and high mass stars, which was to first assemble a comprehensive list of candidate targets from catalogs in the literature. And those catalogs were brainstormed and determined after conversations with our Science Advisory Committee. Then we developed a scriptable exposure time calculator that would allow us to run those ETC calculations over thousands of objects. I forgot to mention that the initial catalogs for the low mass stars were in the hundreds of candidates, and for the high mass stars, they were in the thousands. So we could not run the ETC on each and every one of those manually. So we developed this wrapper around PineSymfo to estimate preliminary exposure times and gauge which targets could reasonably be observed in Ulysses. And then finally, we narrowed down the final sample based on scientific merit. And this was based on several criteria. The first was the relevance to the parameter space. So for the massive stars, that would be spectral type, luminosity class, special subtypes, rotational velocity. And then for the low mass stars, this was stellar mass, accretion rate, and then star forming region or age. We also considered the availability of ancillary data, and we really leveraged the HST and Fuse archives for this for the massive stars, right? So all things being equal, if a massive star had archival HST or Fuse data, it was selected. We considered the efficiency of observation. So in other words, basically total exposure time. All things being equal scientifically, which one is cheaper to observe? And then finally, we put out a call for community proposals early on and received about a dozen proposals that we took into account for our target selection. And to the extent that we were able, we actually selected those stars that were brought forward by the community. So the outcome of this is 160 ONB stars in 4 galaxies that span a range of metallicity from 7% to 50% solar. These galaxies are the LMC SMC, of course, but also NGC 3109 and Sextans A. We also added 200 ONB stars from the archive in those same galaxies, but also additional low metallicity galaxies, such as IC 1613, more stars in Sextans A. These may not exactly have the modes that we use for Ulysses, but are still very relevant for Ulysses science and were therefore included in the final sample. And then the outcome is really a statistical sample that covers the metallicity, temperature, and luminosity class range that was outlined by the UV legacy report. So you can see here how the Ulysses targets, both archival and actually newly observed, are distributed in terms of spectral type luminosity class. The coverage is pretty good. In the SMC, we just didn't have those very early massive O stars, and which is why you can see there's fewer of those there. But if you add the new Ulysses observations to the archival data, it's pretty uniform, at least 4 stars per bin of spectral type luminosity class for early O and B, and then some coverage for later B stars, but sparser because that was the mandate from the UV legacy working group report. I mentioned that we added a posteriori 83 extra targets that didn't have quite the same modes that were used for Ulysses, but were still very interesting. So those are all in our final database in DR7. For the low mass stars, we settled on 58 T-Tauri stars in 8 star forming regions. So these were for the single epoch survey stars that was amounted to 400 orbits. But in this case also, we added 40 T-Tauri stars from archival observations, mostly in Taurus, but also sparsely in other star forming regions. So you can see in this table here, these are the targets that we observed as part of Ulysses, 58 of them distributed in different star forming regions. And then on the right here, you can see the parameter space coverage in terms of accretion rate and stellar mass, including all the archival targets that were pulled into the final sample. So in terms of age, we go from 0.8 to 10 megayears, stellar mass 0.02 to 4 solar masses, and accretion rate is basically negligible all the way to 10 to the minus 5 solar masses per year. We also have this monitoring component that I was mentioning. So for that, we selected 4 stars that were really well studied in the UV, so we could have a good handle on the UV flux and nail down our exposure time since we invested 100 orbits into those. So those 4 stars ended up being TW Hydra, BP Tau, RU Loop, and GMORIG. And I am always very excited to see this movie of the time series that we produced as part of these monitoring observations. They're pretty mesmerizing, and you can see the huge variability in the UV for these monitoring stars. And then Joe Taylor will speak to the data products, I think, later this morning. Big movie. Okay. So in terms of observing strategy, we had very good hints of that in the UV legacy report, but we did have to, the devil's always in the details, and so that's what I'm here to talk about. So the goal for the massive stars was to observe all the O and B stars from 1140 to 750 angstroms, and we did that with a combination of COS and STIS. We really optimized the distribution of the observations between those 2 instruments to, 1, ensure that the science goals were met, but 2, also preserve the lifetime of the COS instrument. And so in terms of exposure times, I think it ended up being roughly 50-50. So the fainter stars were observed with COS, the brighter ones with STIS. Below 1150 angstrom, we actually have pretty decent coverage either with FUSE from archival data or with the blue modes on COS, the 1096 mode that was implemented over 10 years ago now. And this is only for the brightest O stars. For supergiants that were later than 09, we needed to cover the aluminum-3 forest, and so we added near UV coverage with STIS, the E230M 1978 sun wave. And then for yet later B supergiants, B5 and later, we also added longer wavelength coverage with STIS as well. For the low metallicity stars in NGC 3109 and Sextans A, we favored the wavelength coverage over spectral resolution. And so observe those with the G140AL 800 setting that goes down all the way to 900 angstroms and up to 1800 angstroms. So you can see on the right here what it looks like for the different types of stars that we included in the sample. For the T-Tauri stars that was already mentioned, right, the observations actually covered all the way from the FUV to the near-infrared. FUV at medium resolution with COS, a combination of 2 sound waves to cover the molecular feature at 1600 that Noia mentioned. And then near UV through near-infrared with STIS at low resolution. For the monitoring star component, so these were done only with the G160M on COS and G230L on COS as well. So the wavelength coverage is a little shorter, but that was covered also with the G160M setting and G230L. We included 2 sound waves in the UV to be able to correct for vignetting on the left side of FUVB. So all the data products that you may download actually have that correction in, so you don't need to worry about it. And in terms of cadence, so we had 100 orbits for 4 stars, and so we performed 2 epochs of observations separated by about a year, and each epoch included 12 observations spread across 3 rotational periods, and that is in order to both sample the rotation of the star and the accretion variability and be able to disentangle the 2. In addition to the HST observations, the implementation team at STSCI took the lead on a large LCO program to perform for most of the targets we actually